Stage 1 of properties of curves. We're starting out talking about finding the equations for tangent and normal lines. We've talked a lot about drawing them. Now we're going to find out how to write the equation for them. We're going to start with our old friend, point-slope form. Remember point-slope form? Basically, it needs three ingredients. It needs the x and y coordinates at some point of the curve, and then it needs the slope at that point that you want. Okay, so let's take a look at this drawing here. We have this black curve. If you remember, the tangent line is a line which goes in the direction of the curve and touches only at one point. And the normal line is perfectly perpendicular to that red line. Okay, so let's write down the equation for this red line using point-slope form. So basically what we need to do is we need to fill in these three ingredients, x1, y1, and m. Okay, x1 is the x-coordinate of this point of contact. We're going to say it's a, just to be general. Okay, to find the y-coordinate of this point, we would plug a into the function, and we would get f of a. So there's the y-coordinate. So that's y1. This is x1. Finally, we need the slope of the red line. How do we find the slope of the red line? Slope is the derivative, right? So we find the derivative of the original function, f dash, and then we plug in the a value, and that would give us the slope that we want. So we're going to plug in these three ingredients into our point-slope form. So the y1 comes from f of a. The slope, m, comes from f dash of a. And then the x1 comes from a itself. So there is our equation for the tangent line. Remember that the x and the y you do not replace with anything. Once you replace x and y, it ceases to be the equation for a line. And the whole point of this is to have an equation for a line. Okay. At what angle is the normal line relative to the tangent line? They're perpendicular to each other, so they're at 90 degrees to each other. Write the gradient of the normal to the curve at x equals a in terms of f dash of a. Okay, so what about the green line? The green line, we could also write the equation for that. And of course, the x1 and the y1 coordinates are going to be the same because it goes through the exact same point of contact. What about the slope of the normal line? Remember, the normal line is perpendicular to the tangent line. So the tangent line slope is f dash of a. The normal line slope would be the slope that is 90 degrees to that. I don't know if you remember, but the way you find that slope is you do the negative reciprocal of that slope. So we just do -1 over f dash of a. And that would be the slope of the normal. So we're going to put that here. We're going to write -1 slash f dash of a. That is the gradient of the normal at x equals a. Okay, let's do a couple problems. I think it's easier to understand how to do this and see that it's not so bad if we do real problems without so many variables. Remember that we are going to use point-slope form. So one of the things that's useful to do at the beginning of doing these problems is to write out point-slope form. If you do this on the exam, sometimes that'll already get you a point. The first ingredient, which is usually the easiest to replace, is x1 because it is the x value that usually they give you as a reference. So you just put 2 in for x1. That's already one ingredient replaced. The other two ingredients are usually a little bit more challenging and sometimes confusing. Okay, remember that we have two functions that we're going to work with. The original function, which usually they give you, and the derivative function, which we need to find ourselves. Now, the derivative function, why do we need the derivative function? Because remember, in order to find the m, we need to have the derivative and plug in our a value. So let's find our derivative. Remember, the derivative of 1x is 1. The derivative of -2x squared would be -2 times 2x to the first. And the derivative of plus 3 is 0. So simplifying, our derivative is 1 minus 4x. Okay, and remember that in order to find the m value, we actually need to find it at the value x equals 2. So it's not enough just to take the derivative. We need to plug x equals 2 into it. So it would be 1 minus 4 times 2, which is equal to 1 minus 8, which is equal to negative 7. Now that we have a numerical value, now we can put that in for m. Last of all, what about y1? y1 is pretty straightforward. You've known how to do that since 8th grade. You have a function. You have the x value. You put the x value into the function. That gives you the corresponding y value. So let's do that. Y equals 2 minus 2 times 2 squared plus 3. So that is 2 minus 8 plus 3, which is equal to negative 3. So our y1 value is negative 3. Be careful because this is y minus negative 3. Let me rewrite everything with the value substituted in. Y minus negative 3 equals negative 7 times the quantity x minus 2. Okay, now we can definitely simplify this by writing y plus 3, but otherwise we're kind of done. We can leave it in point slope form. If they ask you to find it in slope intercept form or something, you would need to solve for y or rearrange it. But that's good, okay? Let's go to the next one. Same thing, we have a function. We have a specified x value. We are going to use point slope form because we're going to find the tangent line equation, right? We're going to find the equation of the tangent. We need 3 ingredients. One of them we already know, it's x equals 1, okay? The other 2, we need to find the y value. All we need to do is plug x equals 1 into the function. That would give us our y value. Why don't we just do that right now? So 1 cubed minus 5 times 1 is 1 minus 5, which is equal to negative 4. The negative 4 gets put into y1. Last of all, we need to find the slope. We find the slope by finding the derivative, and that's why this process is in this chapter, right? This is a calculus problem because we need to take the derivative to find the slope. And we're just going to do power rule on each one of these. So we get, we get 3x squared minus 5. And that is not all we need to do. We need to plug in our x equals 1 value in order to get a specific slope, which is what we need for the equation of a line, right? You can't have a variable slope for a line. 3 times 1 squared minus 5 is equal to 3 minus 5, which is equal to negative 2. Oops. There we go, right there. Okay, so let me fill everything in. Y minus negative 4. It's a good habit to put things in parentheses when you substitute them in. It keeps you from algebra mistakes. So let's combine this into a positive. So y plus 4 equals negative 2 times x minus 1. Okay? All right. Next one. Y equals 3 over x minus 1 over x squared at negative 1 comma negative 4. This is different, right? Before they would always just give us the x value. Here they gave us a coordinate pair. Remember, this is our x coordinate and this is our y coordinate. So they're actually giving us more information than they gave us before. They gave us both x and y. So that eliminates one of the ingredients that we need, right? Because we are going to, once again, fill in point slope form, but they already gave us the x1 value and they already gave us the negative 4 for the y1 value. So the only thing we need now is the derivative, and then we're going to plug in x equals negative 1 just so that we can find out the numerical value that we can put in for m. Okay? All right, so first we're going to rewrite this because this is hard to take the power rule of these two because the x's are in the denominator. So let's put them in the numerator by using negative exponents. So all I'm doing right now is I am rewriting this function again and using negative exponents so it's easier to take the power rule of. Now that we've rewritten it, let's do the power rule. Coefficients just stay. The exponents come down and get lowered by 1. coefficients stay, exponents come down, and the exponent gets lowered by 1. Okay, so here is our derivative function. If we want, we can simplify it a little bit. How's that? Now we're going to substitute in our x value, which is x equals -1. Notice, even if we have the y value doesn't help us find the derivative value. The x value is the one that does that. Okay, maybe the negative exponents might confuse you, so I'm going to rewrite it with denominator values without negative exponents. See what I did there? I just took the negative exponents and I made them into positive exponents by putting them in the denominator. The first term is -3 because the bottom of -1 squared disappears, it's just 1. And then the second one becomes -2 because -1 cubed is -1. So 2 divided by -1 is -2. So our slope value is -5. Now we can just substitute everything in. Y minus -4 in parentheses. The slope value is -5, and then x minus x1. x1 is -1. So we got y plus 4 equals -5 times quantity x plus 1 is our equation of the line. Okay, let's go down and do the last couple problems. Now we're going to work with normal line equations. So the only thing different is instead of inserting the derivative value with the x value plugged in for our m, we are now going to use a perpendicular m. So it would be -1 over the derivative with a plugged in. Okay, so I think it's easier to show you than to talk about it. So let's just get to it. So the first one says the function is x squared and the point is 3, 9. So they're giving us the x1 and they're giving us the y1. We just need to find the slope, which is going to be -1 over the derivative with our x1 value plugged in. Remember, our x1 value is 3 as they gave it to us. Okay, so our derivative is going to be 2x. When we find the specific value of it, we plug in x equals 3 into it, and that would give us 2 times 3, which is 6. So our tangent line equation would have a slope of 6. Our normal line would have -1 over 6. So that's going to be our slope. I'm just going to rewrite the point slope form. And I know that I'm going to put 3 in for x, and I'm going to put 9 in for y1. I'm sorry, x1, and 9 in for y1. And remember, the slope is going to be -1 over 6 because it's -1 over the derivative with 3 plugged in. So it's going to be y minus 9 equals -1/6 x minus 3. And so this is our normal line equation for 2a. What would have been the tangent line equation? The only difference would have been, instead of -1 over 6, it just would have been 6, right? This would have been the tangent line equation, and this is the normal line equation. Okay, next one, we're going to do one more normal line equation. Once again, we are going to start with the point slope form. Point slope form is written in the formula booklet, so you don't have to memorize it, but after you finish this unit, I'm sure you're already going to have it memorized. We have the x1 and the y1 value already. So now all we need to do is find the slope value. We need to first find the derivative of this function. I am going to first rewrite the function without x's in the denominators. I'm going to put x to the -1/2 instead of square root of x in the bottom. And then I'm also going to put x to the 1/2 instead of square root of x because it's easier to do the power rule this way. All I've done so far is rewritten the function. So I need to actually take the derivative now. Coefficient stays, the exponent comes down, and then you reduce the exponent by 1. Remember, -1/2 minus 1 would be -3/2. The next one, we would there's no coefficient. We bring down the exponent, and then we lower the exponent by 1. 1/2 minus 1 is negative 1/2. Now let me simplify a little bit. Negative 5/2 x to the negative 3/2 minus 1/2 x to the negative 1/2. There's my derivative. I'm going to plug in x equals 1 to see what the y value should be. Oh, not what the y value should, what the derivative value would be at x equals 1. We're going to do that. Let's see, negative 5/2, 1 to the negative 3/2 minus 1/2, 1 to the negative 1/2. Now, these negative exponents might be confusing, but remember, 1 to any power, no matter how weird it is always going to be 1. So I know that my answer is negative 5/2 minus 1/2 equals negative 6/2, which is equal to negative 3. So our slope for the tangent line would be negative 3. What about for the normal line? The normal line slope would be negative 1 over negative 3, which would be positive 1/3. So we just put the 1/3 in for m. So now we can fill everything in. We have x1, we have y1, and we have the m value. Let's fill it in. Y minus 4 equals 1/3 times x minus 1. There is our normal line equation. All right, last problem. Find the equations of the horizontal tangents to this huge function here. So what does that mean? That means that we want to know, are there horizontal tangents to this function? What does that mean? Horizontal tangents would be tangents with slopes of 0, right? That occurs, remember, from the investigation at minimums and maximums. So basically we want to know, when does this have a derivative of 0? So first thing we're going to do is we're going to find the derivative. We find the derivative just by doing power rule. Coefficient stays, 3 comes down, reduced by 1. Coefficient stays, exponent comes down, reduced by 1. Coefficient stays, x disappears, and we're done. Now let's simplify a little bit. 6x squared plus 6x minus 12. We want to know when the derivative equals 0. That would give us the x values when the gradient is 0 for the function, which is what we want to know. That's where the horizontal tangents are. And then we want to actually find the equations of the horizontal tangents. But the first thing we need to do is we need to find out when those horizontal tangents occur. So which x values? So we're going to set this equal to 0, and we're going to solve for x. I think it's easier if we factor out the 6. Oops. Okay, 6 factored out, that would leave us with plus x squared plus x minus 2 equals 0. If we factored this, it would end up being something like this, except this is going to be plus and this is going to be minus. Okay, you can do this with quadratic formula. You don't have to do factoring. I'm not going to teach you how to factor, but feel free to use quadratic formula. So let me check to make sure that this is correct. If I multiply this, I would get 2x. If I multiply this, I would get negative 1x, and that gives me the middle term, so it is correct. What are the two x values which give me a value of 0? It would be x equals negative 2 or x equals positive 1. So those are the two solutions. So there's two places where this function has a gradient of 0. X equals negative 2, x equals 1. How do we find out what the equations of the horizontal tangents are? What we're going to do is we're going to use, you guessed it, point-slope form. We're going to use point-slope form, and we're going to plug in our x1, y1 values. And actually, what about our m value? Our m value is, since it's, derivative of 0, is 0. So actually, when we plug in our 0 here, the whole right side disappears, and we're left with y minus y1 equals 0. So what we really want is our y1 value. Okay, so what we want is what y value corresponds to x equals negative 2, what y value corresponds to x equals 1. Let's find the 1 first, because that's a little easier. If I put 1 in here, 1 in here, 1 in here, it would just be 2 plus 3 minus 12 plus 1, right? So that would be 5 minus 12 is negative 7, plus 1 is negative 6. So one of our y1 values is negative 6. It corresponds to x equals 1. So that means one of our horizontal tangents would be y equals negative 6. The other one would correspond to x equals negative 2. This one's a little harder. If I plug that into here, I would get y equals 2 times negative 2 cubed plus 3 times negative 2 squared minus 12 times negative 2 plus 1. And this would be 2 times negative 8 plus 3 times positive 4. Minus 12 times negative 2 is positive 24 plus 1. So this would be negative 16 plus 12 plus 25, which is equal to negative 4 plus 25, which is equal to 21. Sound right? Okay, so one of our lines would be y equals 21. So there are two lines which are tangent to this original function. They didn't ask us for it, but the x value that corresponds to this tangent would be x equals 1, and the x value that corresponds to this tangent would be x equals negative 2.